Hello everyone. Today we will study the substitution rule. Before I introduce what it is, let me first recall a topic from last semester called differentials. Let y equal to f of x be a differentiable function. The derivative of the function is dy over dx equal to f prime of x. This can be written as dy equal to f prime of x times dx. You can think of we multiply both sides by dx. You can think of this, we multiply both sides by dx. In this expression, dy is called the dependent differential. dy is called the dependent differential. And dx is called the independent differentials. In general, dy depends on dx, so that's called dependent differential. dx is called independent differential. We can plug in any value for dx, then we can find a value for dy. That's called dependent differential. And dx is called independent differential. Next, let's look at some simple example. Find the differentials for each of the following functions. Find the differentials for each of the following functions. First example, y equal to 2x squared plus 6x minus 3. Find the differential means we write dy on the left side, find expression which has dy on the left side and then dx on the right side. So use this formula here. On the left side, I get dy. On the right side, it's f prime times dx. So I take derivative for x here. I get 4x plus 6 times dx. That's called the differential of these functions. And in this formula, dy is called a dependent differential, dx is called an independent differential. Another example, u equal to 3x to the power 4 minus 4x squared minus 5x. In this example, we treat u as a function of x. So on the left side, we write du. On the right side, it's f prime of x dx. Take derivative for x. That's 12x cubed minus ax minus 5 times dx. That's called the differential of this function. Next, u equal to sine x. Find the differentials. So on the left side, I have du. On the right side, take derivative from the function and times dx. Take derivative for sine x, it's cosine x times dx. So that's the differentials of this function. Next example, u equal to tangent of x plus 2x. Find the differentials. Here on the left side, we write du. On the right side, that's f prime of x dx. So take derivative for x, I get secant square x plus 2 times dx. That's how we find the differentials. Next, let me show you an example about derivative. The f of x equal to sine of 2x squared plus x minus 1. Then its derivative, f prime of x, is what? When we have a function inside another function, we can use chain rule. Chain rule says we take derivative from the outside function first. Derivative of sine is cosine. Then keep the inside function the same. Next, times the derivative of the inside function, which is 4x plus 1. So this is the derivative of this function. My next question is, how do we find the antiderivative of this function? Cosine of 2x squared plus x minus 1 times 4x plus 1 dx. How do we find the antiderivative of this function? We know that since this function is the derivative of this function here, upper function here, when I take antiderivative, it must go back to this function. It must go back to original f of x. But how do we go back to there? How do we go back to there? How do we take this antiderivative and go back to this function? So, in order to solve this integral, we're going to use substitution rule. In order to solve the above integral, we need to use the substitution rule. Next, let me introduce the substitution rule. Let f be a continuous function. And let capital F be an antiderivative of lowercase f. So the antiderivative of lowercase f is capital F of x. In general, we won't take antiderivative at constant c. And the derivative of capital F will be lowercase f. Next, let me introduce another function called function g. Let g be a differentiable function. Then, how can we find the derivative? Capital F of g of x. How can we find this derivative? Capital F of g of x. Here, when we see a function inside another function, we can consider chain rule. When we see a function inside another function, think of chain rule. So for chain rule, let the inner function be u. Let u be g of x. Then this function can be rewritten as derivative of f of u. Let u be the inside function. Then take derivative. We take derivative from the outside function first. When we take derivative for capital F, I get lowercase f. So I get f of u. Keep the inside function the same. Then times the derivative of the inside function. What's the derivative of u? Derivative of u here, du over dx is g prime of x. Derivative of u is g prime of x. Next, we can replace u with g of x. We get f of g of x times g prime of x. So this is the derivative of f of g of x. This is the derivative of f of g of x. Which means, since this is the derivative of capital F g of x, which means if I take antiderivative for this function, f of g of x times g prime of x, if I take antiderivative for this function, I must go back to this function. Since this is the derivative of f of g of x, if I take antiderivative for this function, I must go back to this function here. I must get capital F of g of x. Plus c. But how can we go from here to here? We know this must be the answer. But how can we show the work go from here to here? Think of this. Integral f of g of x times g prime of x think of this u. If I let u be g of x, if I let u be g of x, I have integral f of u times g prime of x here, times dx. Now, this integral contains two variables. How can we simplify this expression here? How can we simplify g prime of x dx? How can we simplify g prime of x dx? It looks like a part of this equation here. It looks like a part of this equation here. So if we find the differentials in this equation, we have du equal to g prime of x dx. Here we can see that this part, g prime of x dx, looks exactly the same as du. So this integral can be rewritten as integral of f of u du. Now can we solve this integral? We know that the integral of lowercase f is capital F. The integral of lowercase f is capital F. Integral of lowercase f is capital F. We get f of u plus c. And u is g of x. Replace u with g of x. I get f of g of x plus c. That's exactly the same as what we have here. So here we can see that for integrals in this form, I can always substitute u and du to make the integral simpler and solvable. However, this is an indefinite integral. What if we have a definite integral in this form? What should we do? What if we have a definite integral in this form? Integral from a to b, f of gx times g prime of x. What if we have a definite integral in this form? What should we do? If we try the substitution rule, if we do the same thing, if we do the same substitution, we have f of u, g of x is u, g prime of x times dx is du. Then what should we do for the limits here? What should we do for the upper and lower limit? What should we put here? Can we try a and b here? Let's try, see if it works. If we try a and b here, when we take antiderivative for f of x, when we take antiderivative for lowercase f, we get capital F, which is capital F of u, evaluate from a to b. If I plug in b, I get f of b. If I plug in a, I get f of a. Is this answer correct? Is this answer correct? How do we verify the answer? Think of this. Let's reconsider this integral. Integral from a to b, f of g of x, g prime of x. What if I take antiderivative first? What do we get? What if I take antiderivative for this function? What do we get? We know that derivative of f of g of x is this function, which means if I take antiderivative for this function, I get capital F of g of x. If I take antiderivative for this function, I get capital F of g of x. So if I take antiderivative first, I get f of g of x. Evaluate from a to b. Then if I plug in b, plug in a, it's f of g of b minus f of g of a by evaluation theorem. This is true by evaluation theorem. And this we are not sure. Here we can see that the answer are not the same. This is not true. This is true by evaluation theorem. This is always true. For an antiderivative, plugging upper and lower limit, we get an answer. This is always true. And this one we are not sure. Here we can see that it's not true. This is not true. Then how can we fix this problem? How can we fix this problem? By comparing the answer here, we can see that it should not be b here. It should be g of b here. How can I put g of b here? If this entry here is g of b, then upper limit here must be g of b. If this upper limit is g of b, then this upper limit here it must be g of b. And similarly, for f of a here, if we try to match f of g of a, then this a must be g of a, which means the lower limit must be g of a, and this must be g of a here. So this is not true. In general, the upper limit must be g of b, lower limit must be g of a after substitution. So integral from a to b, f of g of x times g prime of x dx. After substitution, we get f of u du. The upper limit must be g of b, and the lower limit must be g of a. After substitution, upper limit must be g of b, lower limit must be g of a, which means I plug in upper limit b, I plug in b into function g here, plugging b into function g, and then plugging a into function g. I get g of b and g of a. That's an upper and lower limit here. Then, if we take antiderivative, antiderivative of lowercase f is capital F. We get f of x. Evaluate from g of a to g of b. Then, by evaluation theorem, I plug in g of b, plug in g of a, and subtract, we get this. Plug in g of b, then plug in g of a, and subtract, we get this. So, when we make substitution for definite integral, we must change the limit at the same time. Now, let me put a substitution rule here. Let f be a continuous function, and then u equal to g of x. If g is differentiable, and g prime is continuous, then integral f of g of x, g prime of x dx can be written as f of u du, which means I replace g of x with u, replace g of x with u, and replace g prime of x dx with du. And for the definite integral, from a to b, f of g of x times g prime of x dx, I first of all replace b with g of b, then replace a with g of a, then replace g of x with u, then replace g prime of x dx with du. That's a substitution rule for definite integral and indefinite integral. Now, next, based on substitution rule, let's answer this question here. How do we find the integral cosine of 2x squared plus x minus 1 times 4x plus 1 times dx? How do we solve this integral based on substitution rule? Integral cosine of 2x squared plus x minus 1 times 4x plus 1 dx. Based on substitution rule here, how do we solve this integral? So first of all, if I let u be this function here, if I let u be 2x squared plus x minus 1, then the differential du is 4x plus 1 dx. If I substitute, I get cosine of u, this is u, I get cosine of u times what? 4x plus 1 dx is du. So I get cosine of u times du. If I substitute, I get cosine of u times du. Then take antiderivative for cosine of u. Antiderivative of cosine of u is sine of u. And when we take antiderivative as c, then for the final answer, replace u with 2x squared plus x minus 1. I get sine of 2x squared plus x minus 1 plus c. That matches what we have here as function f. The antiderivative of this function is this function. And in the substitution rule, since we usually substitute u into the function, the substitution rule is also called u substitution. Since we usually substitute u, the substitution rule is also called u substitution. Next, let's look at some examples. Evaluate each of the following integrals. First example, integral of 3x squared over 1 plus x cubed squared times dx. How can we solve this integral? In general, when we try to solve for integral, we try to find an antiderivative. If we're able to find an antiderivative directly, put it here, put an antiderivative here at c, and we are done. However, in general, we are not able to find antiderivative directly. So, if we can find antiderivative directly, we should think of some techniques of integration. U substitution is one of the techniques. So let's apply it here. For U substitution, let's first of all make choice for U. What should we choose for U here? Should I let U be the numerator or denominator? In general, there's no rule to choose U. So let's try. Let's first of all try to let U be the numerator, 3x squared. If I let U be 3x squared, then what's my du? Here my du is 6x times 6x. 6x times dx. Now let's try to substitute. Are we able to completely replace all x with u? Let's try. First of all, we can see that the numerator 3x squared is u. How about denominator? How about dx? Here we are not able to substitute all x with u's. So this u substitution won't work. So if I let u be 3x squared, it won't work. Since the numerator won't work, let's try to let u be the denominator, see if it works. The denominator, if I let u be 1 plus s cubed, what's my du? Du will be 3x squared times dx. Now, in this equation here, you can see that the numerator is 3x squared, and we have dx here. In order to substitute du, let me put 3x squared together with dx. So this integral can be rewritten as 1 over 1 plus s cubed squared times 3x dx, 3x squared dx. Then let's try to substitute. If I substitute, I get 1 over, here 1 plus s cubed is u, so I get 1 over u squared. 3x squared dx, 3x squared dx is du. So here we see that we completely replace all x with u's. We completely replace all x with u's. So this u works, this u substitution works. Next, let's solve the integral. 1 over u squared can be rewritten as u raised to negative 2 du. Then take antiderivative using power rule. Add 1 to the exponent, divide by the new exponent as c. U raised to negative 1 over negative 1, it can be rewritten as negative 1 over u plus c. Then for the final answer, replace u with 1 plus s cubed. For the final answer, we can't have u here. We must write it in terms of x. So we get negative 1 over 1 plus s cubed plus c. That's the final answer. So in general, for u substitution, there's no rule to choose u. We have to try. In general, we try the part looks more complicated to be u. We can try, in general, if there are more than one parts, we try the part that looks more complicated to be u. Sometimes it works, but there's no guarantee. Sometimes it works. Usually it works, but there's no guarantee. There's exception. There's no guarantee. If it doesn't work, try to let u be in the other part. For u substitution, there's a lot of trial and error. In general, we first of all try to let the part that looks more complicated to be our u. Next example, integral of x times square root of 5x squared minus 4 times dx. How do we take this integral? Can we find the antiderivative directly? It seems impossible. So let's apply u substitution. What should we choose for u here? Here we have two choices. Either u is x or 5x squared minus 4. In general, try to let u be the part that looks more complicated. So this part looks more complicated. So try to let u be 5x squared minus 4. Next, find du. What's du here? Du here is 10x times dx. Do we have 10x dx here? In this function here, we have x, we have dx, we miss a 10. So what should we do here? We have x and dx, we miss a 10. What should we do? So we can first of all write x and dx together. We have square root of 5x squared minus 4 times x dx. First of all, try to put x dx together. Now, we miss a 10 here. What should we do? If we miss a 10 here, divide both sides by 10. We can divide both sides by a constant. Divide both sides by 10, I get 1 over 10 times du equal to x dx. We can always divide both sides by a constant. Then, if I divide both sides by a constant, I can replace x dx with 1 over 10 du. So let's substitute. 5x squared minus 4 is u. I get square root of u. X dx is 1 over 10 times du. Here, 5x squared minus 4 is u. X dx is 1 over 10 du. Here, we completely replace all x with u's. We completely replace all x with u's. So this u substitution is good. Then we can pull out constant, pull out 1 over 10. Square root of u can be rewritten as u raised to 1 over 2. Then take antiderivative. If we take antiderivative, add 1 to the exponent, you get u raised to 3 over 2 divided by 3 over 2, that's power rule plus c. Then when we have a function divided by a fraction, it's the same as we take the function multiplied by the reciprocal. So we get 1 over 10 times 2 over 3 times u raised to 3 over 2. Multiply. Here I can divide top and bottom by 2. If I divide top and bottom by 2, I get 1 here, 5 here, which is 1 over 15. U raised to 3 over 2. Don't forget plus c. 1 over 15. U raised to 3 over 2 plus c. Then for the final answer, always replace u with 5x squared minus 4. Always when the final answer in terms of x, we get 1 over 15 times 5x squared minus 4 raised to 3 over 2 plus c. That's the final answer. Next example, integral from 1 to 3 x times x squared plus 1 raised to power 3 times dx. How can we solve this integral? Since we are not able to find the antiderivative directly, let's think of u substitution. What should we choose for u here? We have two choices. U could be either x or x squared plus 1. Since this part looks more complicated, so let me let u be x squared plus 1. Then find du. Here du is 2x dx. In the function here, we have x dx. We are missing a 2. So I can first of all put x dx together. I can first of all put x and dx together. Since we miss a 2, 2 is a constant, I can divide both sides by 2. So I get half of du equal to x dx. Then substitute. X squared plus 1 is u, so I get u raised to power 3. X squared plus 1 is u, so I get u raised to power 3. X times dx is half of du. So here we completely replace all x with u. So this substitution is good. Next, how about limit? How about limit? This is a definite integral. How about limit? We cannot use 1 and 3 here. Don't put 1 and 3 here. So what should we put here? In general, for definite integral, we change b to g of b, change a to g of a, which means we're plotting a and b into function u here. We're plotting a and b into function u. So here we're plotting the upper and lower limit into function u. If I plug in 3 for x, 3 squared plus 1 is 10. If I plug in 1 for x, 1 squared plus 1 is 2. That's our new limit. Then I can pull out half. Integral from 2 to 10 u cubed du. Next, take antiderivative. U to the power 3, here we use power rule. We get u raised to power 4 over 4. You evaluate from 2 to 10. If I simplify, I can make it 1 over a times u to the power 4, evaluate from 2 to 10. If I plug in 10, 10 to the power 4 is 10,000. If I plug in 2, 2 to the power 4 is 16. Then we get 1 over a times 10,000 take away 16. That's 9984. And 1 over a times 9984 is 624. That's the answer to this integral. Next example. Integral from 0 to 3. Square root of 5x plus 1 dx. Since we can't find the anti-derivative directly, think of u substitution. Here, what should we choose for u? Here, the only choice for us is 5x plus 1. That's the only choice for us. So let u be 5x plus 1. Then find du. Du is 5 dx. Du is 5 times dx. We have dx here. We are missing a 5. So I can divide both sides by a constant. Divide both sides by 5. I get 1/5 du equal to dx. Then I can substitute. 5x plus 1 is u. 5x plus 1 is u. Dx is 1/5 du. Dx is 1/5 du. Then how about the upper and lower limit? When we do u substitution, we have to change the upper and lower limit at the same time. When we do u substitution, when we change it from x to u, we need to change the upper and lower limit at the same time. So I plug in 3 to function u. Plug in 3 for x. 5 times 3 plus 1 is 16. If I plug in 0, 5 times 0 plus 1 is 1. Then I can pull out 1 over 5. That's a constant. I can pull it outside. Square root of u can be rewritten as u raised to a half times du. Then take antiderivative. Use power rule. Add 1 to the power, divide by the new power. Evaluate from 1 to 16. Then let me simplify this integral here. We'll have a function divided by a fraction. It's the same as saying take a function times the reciprocal. So we have 1/5 times 2/3. U raised to 3 over 2. Evaluate from 1 to 16. 1/5 times 2/3 is 2 over 15. Then plug in 16, plug in 1, take difference. If I plug in 16, 16 raised to 3 half is 64. If I plug in 1, 1 raised to any power is 1. I get 2 over 15 times 63. Then for 63 and 15, I can divide both of them by 3. If I divide both of them by 3, I get 2 over 5 times 21. 2 times 21 is 42. So the final answer is 42 over 5. That's the answer to this integral. Next example, integral of cube root of 1 minus 2x times dx. How can we solve this integral? Since we can't find the antiderivative directly, let's think of u substitution. For u substitution here, the only choice for us is 1 minus 2x. So let u equal to 1 minus 2x. Next, find du. What's du here? Here du is negative 2 times dx. Now, observe this integral here. We have dx. We miss a negative 2. We don't have negative 2 here. Then what should we do? I can divide both sides by negative 2. If we miss a constant, we can divide both sides by negative 2. So I get negative half du equal to dx. If we miss a constant, we can divide both sides by the constant. Then substitute. When we substitute here, 1 minus 2x is u. So I get cube root of u. Dx is negative half du. So here we completely replace all x with u's. Next, I can pull out negative 1 over 2. Cube root of u can be written as u raised to a third times du. Then take antiderivative. For u to a third, I add 1 to the exponent, okay, u raised to 4 third divided by 4 third plus c. Then when we have a function divided by a fraction, take the function, multiply by the fraction. That's a little easier. So I have half times 3 over 4 times u raised to 4 third plus c. Then multiply the fraction. Negative half times 3/4 is negative 3 over a. Then, for the final answer, always replace u with a function of x. This u here is 1 minus 2x raised to the power of 4 over 3 plus c. Next example, integral of s plus 1 times sine of s squared plus 2x plus 3 dx. How do we solve this integral? Since we can't find the antiderivative directly, think of u substitution. What should we choose for u? Here we have two choices. We can let u be s plus 1, or we can let u be s squared plus 2s plus 3. Let's try. Usually try to let u be the part that looks more complicated. Here, this part looks more complicated. So try to let u be s squared plus 2x plus 3. Then what's the u here? Since u is s squared plus 2x plus 3, du is 2x plus 2 times dx. But we don't have 2x plus 2 here. What should we do? We don't have 2x plus 2 here. What should we do here? Observe the right side. 2x plus 2. We see that here 2 is a common factor. If I pull out 2, what do we get? If I pull out 2, we get 2 times s plus 1 dx. So s plus 1 match this term here. So I can divide both sides by 2. Since we missed the 2, I can divide both sides by 2. I get half of du equal to s plus 1 times dx. Then in the integral here, I can write s plus 1 and dx together. We try to write s plus 1 and dx together. This integral can be rewritten as sine of s squared plus 2x plus 3 times s plus 1 times dx. Then let's substitute. If I substitute, s squared plus 2s plus 3 is u. So I get sine u. And s plus 1 dx is half of du times the half of du. Here we completely replace all x with u's. So this u is a good choice. Next, I can pull a half. I get integral of sine u du. Take antiderivative. Antiderivative of sine u is negative cosine u plus c. Then I can multiply half and negative cosine u, which is negative half cosine u. For the final answer, always replace u with a function of x. Here u is s squared plus 2x plus 3. Substitute back. U is s squared plus 2x plus 3 plus c. That's the final answer to this integral. Next example, integral from 2 to 4, 1 over 2s minus 1 squared times dx. How can we solve this integral? Since we can't find the antiderivative directly, let's think of u substitution. What can we choose for u here? In this integral, the only choice is 2x minus 1. That's the only choice we have. Let u be 2x minus 1. What's du? Du here is 2 times dx. Now observe the integral. We have x. We miss a 2. So I can divide both sides by 2. We can always divide both sides by a constant. Here I divide both sides by 2. We get half of du equal to dx. Then substitute. When I substitute, 2s minus 1 become u. So I get 1 over u squared. Dx is half of du. Dx is half of du. Times half of du. Dx is half of du. Here we completely replace all x with u's. Next, the limit. When we change the variables, we need to change the limit at the same time. For any definite integral, when we change the variables, we need to change the limit at the same time. So plugging both 4 and 2 into the function of u. Plugging both 4 and 2 into the function of u. If I plug in 4 for x, 2 times 4 is a minus 1 is 7. If I plug in 2 times 2 is 4, 4 minus 1 is 3. Next, simplify the integral. I can first of all pull out half. Integral from 3 to 7. 1 over u squared can be rewritten as u raised to negative 2 times du. Then, take antiderivative. When we take antiderivative for u raised to negative 2, add 1 to the exponent, divide by the new exponent. Evaluate from 3 to 7. This expression here looks too complicated. Let's simplify first. Before I substitute 3 and 7, let's simplify first. I can first of all pull out negative sign. I get negative 1 over 2. U raised to negative 1 is 1 over u. U raised to negative 1 is 1 over u. Evaluate from 3 to 7. If I plug in 7, I get 1 over 7. If I plug in 3, I get 1 over 3. Here I get negative 1 over 2 times this. And here, for the common denominator, 3 and 7, common denominator is 21. For the first fraction, multiply top and bottom by 3. We get 3. For the second fraction, multiply top and bottom by 7. We get 7 on the top. So we have negative 1 over 2 times negative 4 over 21. For 4 and 2, I can divide both numbers by 2. If I divide both numbers by 2, I get 2 over 21. And double negative become positive. So the final answer is 2 over 21. Next example. Integral from pi over 6 to pi over 3. Cosine raised to power 4 x times sine x dx. What should we do here? First of all, we can't find antiderivative directly, so we must think of u substitution. What should we choose for u here? We have cosine to the power 4x and sine x. Let's try. Cosine to the power 4x looks more complicated. Let's try to let u be cosine to the power 4 of x. Then how do we find du? Cosine to the power 4 of x can be written as cosine x raised to power 4. When we take derivative, we will apply chain rule. Apply chain rule, we get 4 times cosine x raised to power 3 times derivative of sine. Derivative of cosine is negative sine times dx. That can be rewritten as negative 4 cosine to the power 3x times sine x dx. Can we completely replace all x with u's? Let's try. Can we completely replace all x with u's? If I substitute, cosine to the power 4 of x is u. How about sine x dx? We are missing negative 4 cosine cube of x. We are missing this part. That means we are not able to completely replace all x with u's. So this substitution won't work. We are not able to completely replace all x with u's. This substitution won't work. Now let's try. Another choice is sine x. If I let u equal to sine x, what do we get? Another choice is sine x. If I let u be sine x, my du is cosine x dx. Now, can we completely replace all x with u's? Let's try to substitute. Sine x is u. How about cosine to the power 4 and dx? We are missing a power 4 here. That means we are not able to completely replace all x with u's. So this substitution won't work. What other choice do you have? Since both choices doesn't work, what other choice do you have? Think of this. Cosine to the power 4 of x can be written as cosine x raised to power 4. times sine x dx. I can try to let u be cosine of x. That's another choice. Let u be only cosine to the power of x. If I let u be cosine of x, what's my du here? My du is negative sine x times dx. We have sine x dx. What's missing is a negative sign, so I can divide both sides by negative 1. What's missing is a negative sign here, so I can divide both sides by negative 1. I get negative du equal to sine x dx. Divide both sides by negative 1. I get negative du equal to sine x dx. Then substitute. If I substitute, cosine of x is u. I get u to the power 4. Sine x dx is negative du. Then for the upper and lower limit, I plug in pi over 3 for x. Plug in pi over 6 for x. If I plug in pi over 3, cosine pi over 3 is half. If I plug in pi over 6, cosine pi over 6 is radical 3 over 2. Then, simplify the integral. I can pull out negative sign. I get negative integral from radical 3 over 2 to 1 over 2 u raised to power 4 du. Take antiderivative using power rule. I get negative u raised to power 5 over 5. Evaluate from radical 3 over 2 to 1 over 2. This expression can be rewritten as negative 1/5 times u to the power 5. Evaluate from radical 3 over 2 to 1 over 2. If I plug in the upper limit, I get negative 1/5 times. If I plug in 1 over 2, 1 over 2 raised to power 5 is 1 over 32. If I plug in radical 3 over 2, radical 3 over 2 raised to power 5 is what? Radical 3 over 2 raised to power 5 is radical 3 raised to power 5 times 2 raised to power 5. Radical 3 raised to power 5 can be written as radical 3 raised to power 4 times radical 3. 2 to the power 5 is 32. Radical 3 raised to power 4. This is radical 3 times radical 3 times radical 3 times radical 3. Radical 3 times radical 3 is 3. Radical 3 times radical 3 is 3. 3 times 3 is 9. So the numerator is 9 radical 3. Denominator is 32. So I get 9 radical 3 over 32. Then multiply. I get negative 1/5 times 1 minus 9 over radical 3 times 32. Then multiply 3 across, top to the top, bottom to the bottom. On the bottom, 5 times 32 is 160. It's the denominator. For the numerator, we distribute negative 1. I get 9 radical 3 minus 1. That's the final answer to this integral. That's the final answer to this integral. Next example. Integral of sine to the power 10 of x times cosine x dx. How can we solve this integral? Since we can't find the antiderivative directly, let's think of u substitution. What can we choose for u? Here, sine raised to power 10 of x can be written as sine x raised to power 10 times cosine x dx. Since this part looks more complicated, let's try to let u be sine x, see if it works. Let u be sine x, then my du will be cosine x dx. So I can substitute, replace sine x with u, and replace cosine x dx with du. So that's a very good choice. Replace sine x with u, I get u raised to power 10. Replace cosine x dx with du. Here we completely replace all x with u, so that's a very good choice. Next, take antiderivative. We get u raised to power 11 over 11 plus c. And for the final answer, replace u with sine x. We get sine raised to power 11x over 11 plus c. That's the final answer to this problem. Next example. Integral of sine of 1 minus x raised to negative 2 over x cubed dx. How can we take this integral? Since we can't find the antiderivative directly, think of u substitution. What should we choose for u? Since this part looks more complicated, the numerator looks more complicated, let me choose u to be 1 minus x raised to negative 2. Let's try this. The u be 1 minus x raised to negative 2. What's my du? Here, if I take derivative, my du is negative 2 times x raised to negative 3 dx. Bring negative 2 to the front and subtract the power by 1. Negative 2 minus 1 is negative 3. Then simplify. If I simplify this expression, what do we get? If I simplify, double negative becomes positive. X raised to power of negative 3 can be written as 1 over x raised to power 3 dx. Now compare what we have here. We have x cubed on the bottom, so this integral can be rewritten as sine of 1 minus x raised to negative 2 times 1 over x cubed times dx. X cubed on the bottom can be pulled out, written as 1 over x cubed times dx. So we have 1 over x cubed dx. What's missing is number 2. That's a constant, so I can divide both sides by 2. If I divide both sides by 2, I get 1 over 2 du equal to 1 over x cubed dx. Then substitute. If I substitute, I get u here. 1 over 1 minus x raised to negative 2 is u. So I get sine of u here. This is u. And 1 over x cubed times dx. 1 over x cubed times dx. That's half of du. This is half of du. So I get half of du here. Next, I can pull out 1 over 2. I get sine u du. Then take antiderivative. Antiderivative of sine u is negative cosine u plus c. Then multiply. Half times negative cosine u is negative half cosine u plus c. Then for the final answer, replace u with 1 minus x raised to negative 2. So we get cosine of 1 minus x raised to negative 2 plus c. That's the final answer. Next example, integral of cosine of 1 over x to the power 4 over x to the power 5 times dx. How can we solve this integral? First of all, since we can't find the antiderivative directly, we need to think of u substitution. For u substitution, what should we choose for u? Here we have two choices. 1 over x to the power 4 or x to the power 5. This fraction looks more complicated. Let's try this fraction here. The u be 1 over x to the power 4. That can be rewritten as x raised to negative 4. Then find du. Du is negative 4 times x raised to negative 5. We bring negative 4 to the front, reduce the power by 1, then times dx. Now, if we simplify this, this can be rewritten as du equal to negative 4 times 1 over x to the power 5 dx. We have x to the power 4 in the denominator, so let's rewrite this integral. This integral can be rewritten as cosine of 1 over x to the power 4 cosine of 1 over x to the power 4 times 1 over x to the power 5 dx. I can pull out x to the power 4 on the bottom, write it as 1 over x to the power 5 times dx. Now compare what we have here. What we have here is negative 4 times 1 over x to the power 5 dx. This part looks exactly the same. What's missing is negative 4. So I can divide both sides by a constant negative 4. If I divide both sides by negative 4, I get negative 1 over 4 du equal to 1 over x to the power 5 dx. Then substitute. 1 over x to the power 4 is u times 1 over x to the power 5 dx. 1 over x to the power 5 dx is this. It's negative 1 over 4 du. Replace negative 1 over 5, negative 1 over x to the power 5. Replace 1 over x to the power 5 dx with negative 1 over 4 du. Here I completely replace all x with u's. That means this substitution works. Then simplify. I can pull out negative 1 over 4. Write it as negative 1 over 4 cosine u du. Here, take antiderivative for cosine u. Antiderivative of cosine u is positive sine u. Then, for the final answer, replace u with 1 over x to the power 4. So the final answer is negative 1 over 4 times sine of 1 over x to the power 4 plus c. That's the final answer to this integral. Next example. Integral of secant square of square root of x over square root of x dx. How can we solve this integral? Since we can't find the antiderivative directly, let's think of u substitution. What can we choose for u? Here, one of the choice is square root of u. Let's try to let u be square root of u, square root of x. One of the choice is square root of x. If I let u be square root of x, what's du? How can we find du here? Square root of x can be written as x raised to 1 over 2. If I take derivative, I can bring half to the front and reduce the power by 1. I get half times x raised to negative half dx. If I simplify, I have 1 over 2 times 1 over x raised to positive half dx. I write x raised to negative half as 1 over x raised to positive half. X raised to positive half is square root of x. It's square root of x. In the integral here, we also have square root of x on the bottom. So this integral can be rewritten as secant square of square root of x times 1 over the square root of x on the bottom times dx. Now compare what we have here. We have 1 over square root of x. We have dx. What's missing is a half. Half is a constant. So I can multiply both sides by 2 to eliminate this half. If I multiply both sides by 2, I get 2 du equal to 1 over square root of x dx. If I multiply both sides by 2, I can eliminate half here. Then this match what we have here. Now let's substitute. I get secant square of square root of x is u. So I get secant square of u. 1 over square root of x times dx is 2 du. Here we completely replace x with u. So this substitution works. Then I can pull out 2. 2 is a constant, pull out 2. I get secant square of u times du. Take antiderivative for secant square of u. Antiderivative of secant square of u is tangent of u plus c. Then for the final answer, replace u with square root of x. For the final answer, replace u with square root of x. We get 2 tangent square root of x plus c. That's the integral. That's the answer to this integral. Next. Integral of secant to the power 3 of x times tangent x dx. How can we solve this integral? Since we can't find the antiderivative directly, let's try to use U substitution. What should we choose for U here? Let's try. In general, there's no rule to choose U. So let's try. Let's first of all try to let U be secant cube. See if it works. If I let U be secant cube of x, what's my du? Secant cube of x is secant x raised to power 3. What's my du here? Use chain rule. Du is 3 times secant x squared, then times derivative of inside. Derivative of secant is secant x times tangent x times dx. If we simplify, my du is 3 times secant x squared times secant x is secant x cube, which is secant cube x times tangent x dx. If we substitute, I can replace secant cube x with u. Then how about tangent x dx? We are missing 3 secant cube x here. So since we are not able to completely replace all x with u's, this u substitution won't work here. So this choice won't work. Let's try a different choice for u. What other choice do you have? Let's try to let u be tangent x. Does it work? If we let u be tangent x, what's the u? Derivative of tangent is secant square of x. So du is secant square x times dx. Can we substitute? Can we replace all x with u's? Let's try. I can replace this tangent with u. So I get u here. How about secant cube dx? We only have secant squared. We only have 6 secant square x here. So we can't completely replace all x with u's. So this substitution won't work. What other choice do you have? We can think of this way. If we think of secant x cube, if we think of secant cube x is secant x cube times tangent x dx. If I let u be secant x, does it work? If I let u be secant x, does it work? Let's try. What's du? Du is secant x tangent x dx. If we substitute, what do we get? If I substitute, I can replace secant x with u. I get u cube. Then, how about tangent x dx? We miss a secant here. How about tangent x dx? We miss a secant here. So it looks like this substitution also doesn't work. Then what should we do? Let's observe carefully. We miss a secant here. But we have 3 secants here. We have 3 secants multiplied together here. What if I take out 1 secant from here? We have 3 secant here. What if I take out 1 secant from here? What do we get? So secant cube x. What if I take out 1 secant from here? If I take out 1 secant from here, I have secant x squared times secant x tangent x dx. Since we miss a secant, I can take out 1 secant from here. Write it as secant x squared times secant x tangent x. Now does it work? Now let's substitute. Secant x is u. So you get u squared. Secant x tangent x dx is du. Secant x tangent x dx is du. Secant x tangent x dx is du. So I completely replace all x with u's. This substitution works. Then take antiderivative. We get u cube over 3 plus c. Then for the final answer, replace u with secant. We get secant cube x over 3 plus c. That's the final answer. That's the answer to this integral. So you can see that for u substitution, there's a lot of trial and error. We try to let u be some terms. If it doesn't work, try to let u be something else. There's a lot of trial and error. In general, there's no rule to choose u. So there's a lot of trial and error. Next. Integral of secant 4x tension 4x times secant to the power 5 of 4x dx. Secant of 4x times tension of 4x times secant to the power 5 of 4x. How can we solve this integral? Since we can't find the antiderivative directly, let's think of u substitution. What can we choose u here? What should we choose u here? Let's try. Secant to the power 4 of 4x can be written as secant to the power 4 of 4x can be written as secant of 4x raised to the power 5 dx. If I let u be secant of 4x, if I let u be secant of 4x, what's my du? Be very, very careful. Here we need chain rule. For secant of 4x, we need chain rule here. When we take derivative, derivative of secant is secant tension. So that's secant 4x times tension 4x. Don't forget chain rule. Times the derivative of the inside function. Derivative of 4x is 4 times dx. That's du. Now let's try to compare what we have here. This is u. Secant 4x, tension 4x, we have it here. What's missing is a 4. What's missing is a 4. So I can divide both sides by 4. Since 4 is a constant, I can divide both sides by 4. I get 1 over 4 du equal to secant 4x, tension 4x times dx. Then let me rewrite this integral. It can be written as secant 4x raised to power 5 times secant 4x tension 4x dx. Now let's substitute. Secant 4x is u. I get u to the power 5. Secant 4x tension 4x times dx is 1 over 4 du. Secant 4x tension 4x dx is 1 over 4 du. Then I can pull out the constant. Pull out constant 1 over 4. The integral of u raised to power 5 du. Take antiderivative. I get 1 over 4 times u to the power 6 over 6 plus c. Simplify, I get 1 over 24 times u to the power 6 plus c. For the final answer, replace u with secant. So the final answer is 1 over 24 times secant to the power 6 of 4x plus c. For the final answer, replace u with secant. We get 1 over 24. 1 over 24 times secant to the power 6 of 4x plus c. That's the answer to this integral.